Good day and welcome to the IEEE Computer Society's presentation on Why Machine Intelligence is Taking Over Cybersecurity by Dr. Scott Miserandino. This webinar is proudly sponsored by BluVector. My name is Amir Drakis and I will be moderating today's presentation. At the end of our presentation, you will have time for questions. As questions occur to you, please take the time to type them into the box provided and press the submit button. You do not need to wait until the end of the presentation to do so. Now I would like to introduce the speaker for today's webinar. Dr. Scott Miserandino leads BluVector's engineering and research team as the product's Vice President of Research and Development. Dr. Miserandino has over 10 years of industry experience, including cybersecurity work at the U.S. Department of Defense and Intelligence community, as well as Northrop Grumman. Without further ado, Dr. Scott Miserandino.
Hello, everybody, and thanks for joining today for this talk on machine learning and cybersecurity. They're two of the hottest fields today in technology, and I've been privileged to work with BluVector in bringing these two fields together, beginning in 2010 and joining the team in 2013 as the chief data scientist. And really seeing from the early days of the application of the machine learning technology to the field of cybersecurity. And for today's talk, I'm going to walk everyone through a little bit of this intersection and try to explain, how I see machine learning being applied and where the real benefits are going to come and how it can be a major game changer in the cybersecurity world. I would like to begin with a little bit of context around sort of the history of cybersecurity and cyber solutions. For those that may not be as familiar with it, cybersecurity and in particular the detection of malicious attacks sort of began with fairly straightforward techniques. The early evolutionary stages, things like signatures and packet filters were readily available and used, throughout many enterprises. They were really good at recognizing known threats. It was all about finding something, figuring out a way to identify it, and then deploying that across to sort of institute a sort of herd immunity. And these are things with like antivirus signatures and some network intrusion detection-based signature systems. As any evolutionary system, adversaries began to adapt to the defensive environment, and they began developing techniques like polymorphism and domain-generating algorithms, other sort of ways of avoiding these very brittle signatures. And then the defenses themselves began to evolve. And here we see the introduction of heuristics and behavioral rules being introduced into the security space. Things like dynamic execution or sandboxing being brought in, where pieces of content would be executed in a safe environment and then monitored for signs of malicious behavior. Again, this technique was really based on still having identified threats and then constructing these rules and behaviors that you would look for in order to identify similar threats, even if their signatures had changed. So in one way, it was an improvement over these signature and packet-based systems. It was a lot less brittle, but still very reliant on having previously identified malicious content before in order to develop those techniques. Again, beginning in the late 2000s, we see the introduction of machine learning into this space with the promise of being able to get ahead of the threat. Right, really move in and not be reliant on having to have found something before in order to be able to detect it for the first time. And this is being driven by other forms of zero-day malware that were coming out, is becoming more prevalent. You start to see the introduction of nation states, or at least the public identification of nation states being involved in some of these cyber attacks. The sophistication of the adversary was growing, and therefore there was definitely a desire to get a more sophisticated defense. And here the promise was you would be able to build this, super intelligent machine that would be able to reason its way through the high volume and velocity of data that is prevalent in the cyber environment. And it would be this sort of like Terminator for cyber defense. And the reality is, while the vision was good, the implementations were maybe a little bit more akin to a simpler robotic life form. But the promises were there. The introduction of machine learning really did bring a set of robust tools and an ability to get a little bit ahead of the threat. But as we're going to discover through the rest of this talk, it didn't really remove all sort of negative or ways an adversary can get around it. There are still some new problems that it introduces that we have to be really careful about when developing these solutions. And that's what we're going to sort of investigate throughout the rest of this talk. And just for those that maybe are familiar with machine learning, there are two big classes of machine learning algorithms and that are getting applied to cyber defense work today. One is the unclassified type, and that's primarily seen in tools that are doing some form of anomaly detection. So if anybody is asking about, how do you establish a baseline and discover behavior that's unusual, these are all point to the need for anomaly detection or describe an anomaly detection-based solution. And so we see this as one of the two largest classes of application of machine learning to the space. The other class is around supervised techniques. And in supervised techniques, the game is typically around classification, most often being applied to particular pieces of content in the network. So this is things like files that could be weaponized and be part of a malware-based attack, anywhere from Windows executables or weaponized PDF files or Word documents. There could even be network streams that can be labeled as being malicious. And the whole supervised technique is really about starting with labeled data that you know the class of. And in cybersecurity, typically that means it's either benign or malicious. Sometimes you do get into doing finer grain classifications and trying to identify maybe types of families of malware. So you do see that as well. But for classification, one of the key things that is required to get the algorithms to work is the definition of a feature space. And features are really sort of the way the machine views the data. It's a lens by which the learning algorithms are actually going to differentiate between the labels that are provided. So tell the difference between benign and malicious. And we have to be really, really careful. This is, I think, the hardest part of this problem is in the data science effort dedicated to this feature engineering space. And here I give a really simplified example of just trying to tell the difference between something that's a duck, not a duck. And one can think of a couple of features that might make sense, just off the top of your head, like it can walk and it can swim and it can quack, then it must be a duck. But as you can see in the not duck categories, there are things that seem to walk and swim and quack that still look like a duck but really aren't. And figuring that out is really the job of the data scientists that are working in this space between machine learning and cybersecurity. They're trying to understand how to make these samples or express these samples in a way to the learning algorithms such that they can actually do high accuracy differentiation between these classes. So this is definitely one of the big challenges in the space, is this feature engineering step. So we're seeing machine learning applied, to address a variety of problems. I talked about two of the largest classes of machine learning algorithms, unsupervised and supervised. There's also two classes of the way the algorithms learn. And these are loosely described as sort of incremental or continuous learning, which means as every new sample is introduced to the algorithm, it adjusts itself, it adjusts the model in a way to account for that new piece of information. And then also batch learning is the other mechanism. And here it's a gathering of all of your samples from which you would want to learn in sort of one time, one place, and then learning all at once and sort of optimizing your model over the complete set. And of course, there's hybrid approaches between these two. But it does, if you look at this sort of four-part breakdown of the space, you could see how different problems are being solved using sort of different combinations of supervised learning and batch learning, unsupervised learning and incremental learning, to cover everything from anomaly detection to malware detection. Probably the oldest application is in spam filtering, malware family identification, and insider threat detection. So we're seeing machine learning get used all over the place. There is, no shortage of companies these days, and a lot of, I would say, noise maybe in the cybersecurity space around what machine learning is and how it's used. And the truth of it is that it's used in a lot of different ways, and there's a lot of nuance into exactly what approaches are being taken to solve what problems. But one, I think, most of the illustrative ways of looking at it is to actually think back to sort of a basic of cybersecurity, and that's the cyber kill chain. So this is the set of events that occur during a cyber attack in a particular sequence. Pretty much any cyber attack usually begins with some sort of delivery of malicious content, often involving some level of exploitation of a vulnerability. That would begin the process of installing or providing access to the adversary to the system, whether that be for purposes of ransom collection or intelligence gathering. Whatever the ultimate mission is, there needs to be some access, unauthorized access to a victim computer. That's typically followed by something along the line of command and control, the adversary interacting with their new asset. Depending on the level and sophistication of the attack and the motivations of the adversary, you then begin to see the latter stages of the kill chain, including lateral movement or the transfer of that control from one system to another within a particular enterprise to gain access to more or better information. Once that information is attained in the adversary's enterprise or in the victim enterprise, often it is staged for later removal, which is termed exfiltration. And then at some point along the lines, someone discovers that this has occurred. And that often kicks off a forensics workflow in order to determine when and to what extent particular damage has been done. So that's, again, just a brief overview of the cyber kill chain. And what I've done is overlaid sort of the approaches or the classes of machine learning on this kill chain, and it really centers around that install step. We see primarily the application of classification techniques, supervised machine learning, to detect the early part of this kill chain, the either pre-breach, near breach, or at breach point of attack. And then we see anomaly detection being used for the latter parts of this kill chain, or the post-breach phases of an attack, where you're focused primarily on that lateral movement, staging and exfiltration, where you're trying to determine, why is something acting differently than it did before. And really sort of the more current emphasis in the market has been around the anomaly detection space, but the earlier capability has actually been around the classification area. Some of the earliest people to bring solutions to the market have been focused in that classification space. But today we hear a lot more about anomaly detection, mostly because there's been a sort of a distrust that's been growing over the ability to do good detection due to the failure of those earlier evolutionary stages of detection, signature-based detection, and heuristic and rule-based detection around dynamic analysis. And so there's been this concept that, oh, you have to be able to watch for post-breach activity. And it's all great, and it works incredibly well together as part of a layered defense strategy. Typically when people talk about layered defenses, they're talking about its location in the network, endpoint versus perimeter defense. But a layered defense concept works just as well in terms of the kill chain. Techniques focused on early stage detection, pre-breach detection, as well as those techniques focused on post-breach detection, and therefore give an enterprise a greater level of security and reduce risk when you can place both together, and both have applications for machine learning there. So like I said, if you guys take anything away from this talk, I hope you take away this image of how machine learning is being used in space today and why it's becoming more and more pervasive, because it can give you both this defense at the early stages of attack and at the post-breach time frame. So that's a little bit of the lesson on machine learning for the cybersecurity guys. Now I'm going to pivot a little bit more for the machine learning lesson for those that are maybe less familiar with the data science side. And here I want to point out that really with any machine learning solution, the data science teams have more or less three big knobs that they can turn in order to build a really good solution. The first knob is the learning algorithm itself. This is the piece of software that is ultimately going to perform or build a model capable of doing anomaly detection or doing classification. The second one is the feature space or feature engineering. Talked a little bit about that earlier with the duck example. This is how the algorithms view the data or the samples, both in the training phase of the model building, as well as in the deployment phase when you're looking at samples of unknown classification or you're monitoring the network for malicious or for anomalous behavior. And then finally, the knob around the training data itself. And as in most machine learning-based solutions, even in other fields, data is king. The ability to have a diverse data set is critical to developing good models. So I'm going to drill down into each of these briefly. So first thing to kind of understand in the learning model space is there's a lot of work that's been done. Machine learning is not a new field per se. It's been around for decades. It has a lot of great tooling that has been invented, and it continues to be invented as new techniques are discovered. So everything from new deep learning areas with artificial neural networks to older school statistical learning, and even everything in between for classification-based solutions. And it runs the gamut of platforms that you can do it on, everything from learning on big data sets in the cloud to doing learning locally within a single box to having distributed learners, again, locally within your enterprise. All of this has been developed through a variety of vendor offerings and is available for use and is leveraged by most of the cybersecurity teams trying to apply these machine learning techniques. A lot of them are not out there building their own learning models. They're really leveraging this incredible toolbox that has been built up over the decades. I did mention classifiers and models, and I know a lot of people on the call may not, have a good picture of what they actually are, what they mean. So here I'm trying to give a view, and I have stolen the graphic of exactly, what are these models trying to do? And here, this is a toy example where we're showing different learning algorithms and how they distinguish between the red dots and the blue dots. And each learning model is basically doing one thing. They're trying to draw a decision boundary in an n-dimensional space. And those set of dimensions are the features. So your feature space is sort of defining the geometry that's possible with the decision boundary, and then the algorithm is actually drawing that boundary in the higher dimensional space. And here's some examples of two-dimensional things. And each algorithm has different properties of the way it can draw that boundary. So dealing with the type of curvature, whether or not it can offer gaps in the boundary or be disjoint boundary conditions. Each algorithm is a little bit differently. So that's why you often see with data scientists is they will take one set of training, one feature space definition, and then throw everything in the toolbox at it to see, what is the best way of, what is the most successful model given those training sets and those features. And they will play around with parameterization of these models in order to fine-tune them. So again, a little bit on just kind of what a model is, what a machine learning-based model is, particularly around the question of classification. The next thing to look at and consider is the feature space itself. So what are some useful features in applying machine learning to cybersecurity? So one set is around sort of static features of content. And I'm going to break this up into two sets of features that are content-based, and then one set of features that is more metadata or stream-based that we see more typically applied with the anomaly detection-based solutions. So for the classification-based solutions, again, they have sort of a choice between static features, which are ones that are available by looking at the binary structure of the content. And the good thing about these features is they're very easy to obtain. And they're very quick to obtain, which means that as we're receiving samples, being able to extract the feature quickly allows you to process many samples very quickly. And the downside of this is that oftentimes both the feature itself can be somewhat opaque as to what it really means. And also there are techniques that adversaries will try to use in order to obfuscate their content or their behaviors from static approaches, things like packers or even encryption. Other forms of obfuscation are available as well. And those are the things that at the feature space level need to be dealt with in the feature engineering phase. But just to give some examples, things like n-grams, these are short binary patterns. Often they need to be used in large numbers to be meaningful. It's very different from a signature. So a signature, while it too is a binary pattern, is often tied to a particular offset and needs to be quite long. Here, the idea is instead that you give a lot of short binary patterns and let the algorithm figure out the best way to combine them to get high reliability detection or classification. The other thing is within cybersecurity, these binary pieces of content aren't just blobs of data. They have known structures. So here are a couple of examples for like a PDF file, and then also a Windows executable file or a PE file. All of these have a structure that one can leverage in order to define better features. And I show a couple of vendors just to show that there's a variety of people in the marketplace using these techniques. None of the lists are meant to be exhaustive. There are hundreds and hundreds of vendors, and today almost all of them will mention some form of machine learning in their solution. So I just want to set out a bit of a disclaimer. The other set of features are dynamic features. So these are based on how a particular piece of content interacts with its environment. This can be done by watching it on the endpoint or the victim machine. It could be done in a sandbox or a more controlled environment. And there are folks doing all of that. And the real difference between the dynamic-based features and the static-based features is how long it takes to actually acquire them. Because for those operating in the sandbox world, you need to be able to actually stand up the sandbox and get the system, the sample to execute in it in a way that you can extract those features. And that often in of itself is a slow process, taking perhaps several, tens of seconds per sample to several minutes, whereas static-based analysis typically can be performed in the time frames of 10 milliseconds to 100 milliseconds per sample in terms of just the feature extraction steps. But the trade-off is in understanding the features that you get out of dynamic analysis typically are a little bit easier for an analyst to understand, and in combination sort of get a sense of what the model has actually learned from the training data. As I mentioned, there's also anomaly detection, and here often the feature spaces used are temporal. Meaning that you're tracking behaviors or counts of activity over time, how many users logged into a particular box, what was the set of users over time, how often has this particular user logged into this particular box or with this particular set of privileges. All of those can be tracked as temporal features over time, and you're looking for simple statistical variation from baseline behavior. But those statistical variations don't always correlate to malicious activity. So these techniques tend to have be a little bit more prone to false positives within the environment. They tend to require an on-site learning phase that's longer than what you can achieve with sort of the supervised learning approaches. But the benefit of it is it can be applied to a different set of problems. As I mentioned, the post-breach analysis problem and also the insider threat detection problem. They're usually well suited for anomaly detection type approaches. So I do want to give you a little bit of a story going into this next section on training data. BluVector, we had built a set of classifiers around the detection of malicious Microsoft Office documents. And we deployed those to a customer in Japan. And we quickly discovered that, our models did not speak Japanese very well and that we had a localization issue. Everything just blew up. All of our lab data said it should have been great. And when we got out there, we started receiving this foreign language documents. All of a sudden, everything just went haywire with the models. And you step back and immediately realize that this was the expression of a bias in our learning set. And again, for those that are maybe being introduced to machine learning the first time here, this, I think almost any data science will tell you, is the bane of their existence. It is a very difficult problem to understand within models, is what is inherent in the way you've collected your training data or in the way you've defined the features relative to the training samples that the learner is picking up on, but really has nothing to do with the problem you're trying to solve. So, like I said, in this example where we try to deploy our Word document classifier in the Japanese language space, we had obviously learned that maybe some English language elements were good, and therefore the lack of them in the Japanese language documents caused those models to erroneously believe more samples were malicious than really were. And that was the expression of this training bias that we have. And there really is a need for data science teams to really watch operational results as you deploy machine learning models into different networks, different countries, to see if their training sets really are diverse enough in order to build very robust models. So as I mentioned, this is one of those things that took us from the Terminator style artificial intelligence down a level or two. And what this does mean is that these models have to have an opportunity to be tailored to their space. And this has been sort of one of the key features of machine learning since its inception in other fields, is that you want a technology that tailors itself to the user, that tailors itself to the enterprise. And just as the machine learning approach produced the problem, it also offers the solution. And this is a big change in the world of cybersecurity, and it has really deep impacts to exactly why machine learning, machine intelligence is going to be a game changer. And the way I like to kind of summarize this is to think about what I call the common model problem in cybersecurity. And a way to look at that is imagine that each of these enterprises as a house or a business, and that your cyber defense, whether it be anomaly detection or classification based, right, is still a model that's getting deployed. And the way that model is being deployed, say it's signature or packet filter based, is everybody gets the same copy. So you build the best signatures you can and you give them to everyone. And if an adversary ever gets a hold of that set, right, they just try to write their malware so that it doesn't trip any of those signatures. And these things are readily available, so that approach is pretty easy for them to do. They just get a hold of the lock, learn how to pick it. And then they're guaranteed that anyone who has that defense, they can get by, because they've already baked that in before it ever even left their development environment. And so when security solutions evolved, the locks basically just got better. But the deployment model stayed the same. We still gave the same locks to everybody. An adversary can still get a copy of the lock, and it was still relatively easy for them to figure out how to pick it. When we started with machine learning, a lot of folks kind of went the same route. We built these models and deployed them to everybody. So everybody would get the same set of models. Again, it's a better lock. But if the adversary got it, they could still brute force this. They could still perhaps even reverse engineer the feature set and ultimately be able to pick that lock. So as I said, this traditional defense is just about moving the quality of the locks from sort of a basic capability to an advanced capability. But what machine learning is going to introduce is the ability to go to this concept of a moving defense. And what I mean by that is that these locks no longer have to be static. Not only do they not have to be static, as in they can change over time, they can also be tailored. They can be different in every environment. And it's not that this is some idea that, brilliant, BluVector just came up with. It's really about the difficulty in having done this before. Because I think if security vendors could do this easily before, they would have. Nobody likes to have a static defense. Everybody would prefer that it'd be much harder for the adversary to predict what they're going to come up against. But before machine learning, this was actually just logistically really hard to do. And it was hard to do because it was difficult to ensure that everybody would get the same quality of lock. Nobody wants to get the second best lock produced out of a particular vendor or solution. Everything needs to be of the same equivalent quality. And again, I think machine learning really is the first technology that allows us to get into that space and will ultimately be a major game changer because of that key feature. So just to give you guys a little bit of a sense of how this works how this works practically, there's a couple of ways to achieve this sort of moving defense concept. One is that the vendor can do some model randomization, right? They can randomly select different data in order to build different models and then deploy those models to their customers in different ways, or different customers with different models. So everybody gets something that is unique. But here there's no diversity in the data sets under that approach. The other approach is that you try to build the differentiation locally once you're on the network. And this can be done in two ways. One, via model reinforcement. So here you're going to take all the things that the model gets right, feed it back in and tell it to retrain. And that's just going to teach it that its biases are absolutely correct. And that it's going to begin to double down on that information. It will alter the locks, but it could cause unintended drift from really good performance. The last approach, and this is the one I think most folks would use, is the one we use, is around corrective reinforcement or negative reinforcement. And this is taking the errors that the model makes. And these are often identified by cyber analysts that are looking at the results of the detection technique. They're in their day-to-day jobs always looking at discarding false positives, discarding false negatives, or trying to find false negatives, if anything got through. And what we would like to be able to do is leverage that workflow that already exists, take that feedback, push it back into the classifier, and then you get two big benefits. One, the feedback is useful in terms of expanding the data set and correcting errors and biases that may exist there. And then two, it does provide for a moving defense. Each model now is different because each environment has added different new data when it has gone through this correction phase. So with that, I just want to summarize here with Bender again and our cross between Terminator and sort of simple machine. Really, machine learning is more than simple, right? It is doing something that can't be done before. It is taking over a lot of the cybersecurity space. It's providing a diversity of defense. It's providing that tailoring to specific environments so that false positives can be reduced, even if the initial distributed model is meant to be as broadly applicable as possible. You could always get a slightly better fit with tailoring. It provides for continuous improvement, reducing error rates, and it doesn't require necessarily that data be shared. Privacy is a key concern. I talked earlier about Word documents, PDF documents. They often contain proprietary information, and the ability to learn from this without having to send that to a vendor for them to detonate in their sandbox and build new rules, or to write AV signatures, or to just tell you that, hey, yeah, that was a false positive, is great. You could do all of this without that exposure of the data, and also do it more quickly because you don't have to wait for them to respond. So definitely a lot of benefits to this technology in the cybersecurity space. This is a little bit on BluVector. Obviously, my background is in the supervised machine learning approach. I try to give anomaly detection. It's due in this talk, and then hopefully you found that section interesting as well. If anybody interested, please check out BluVector.io. And thanks everyone for your attention. I'd be happy to address any questions that you might have.
All right, Scott, yes, we do have a bunch of questions from the audience. If I can go ahead and just go through those one at a time for you. Let's see. Our first question will be, how much resilient machine learning algorithms are for truly novel attacks?
So typically you wouldn't train an algorithm just for novel attacks. You hope the algorithm or the learning model catches a novel attack, but you wouldn't necessarily pick an algorithm just for that purpose. And the algorithms themselves, like I said, are the same algorithms used in every other field. You don't see, the invention of special learning algorithms for cybersecurity. It really is leveraging the same decision tree algorithm that's used for identifying faces and pictures, or artificial neural network in that case is becoming a little bit more popular, that you see in other fields. The algorithms are the same. It really is about that feature definition, and that's the place where cybersecurity is entering into the question, and therefore, if you're interested in just novel attacks, you really want to focus on the feature engineering space rather than trying to build a special learner that only picks up novel attacks. You could also do it on the data side and just say, hey, these things I consider novel, and therefore I want to build a model that detects only those and may even ignore less novel attacks. So again, it really is less about the algorithm that's learning and more about the features that you're selecting and perhaps even how you're labeling your training set.
Great. The next question. Is a static lock or model actually learning what new attacks look like based on the training data, or was not a machine learning method?
Yeah, so this is definitely a great question. So a lot of people are using machine learning. They'll bake a model and then they'll put it into the environment, and once it's there, it's static. It doesn't change. But I still feel it has every right to claim that it's a machine learning based approach because it used machine learning to develop that initial model. But certainly not all solutions actually alter themselves once they get on site. So if you guys are talking, if anyone is talking to either vendors or if you're doing research in this area, you definitely need to ask, what does a particular model do once it's deployed? Does it change? How does it change? Almost all anomaly detection algorithms will change on site. They will learn from their data and baseline. The ones that tend to fall into the category of being very static on site are the classification-based ones, where it's a single deployment, but it doesn't really learn once it's there. All the learning is sort of pre-baked in. But there are techniques that even for supervised approaches, you can learn on site. And I talked a little bit about that in situ capability of being able to use analyst feedback in order to derive new training data for supervised approaches. So it's certainly possible, but not everybody does it.
Perfect, thank you. Next question. Do these kinds of systems that monitor temporal activity correlate benign events to change in user behavior? For example, a company rolls out new employee policies that change their access patterns.
They do after a lot of noise. So what will happen is they usually have a training phase where they will begin to baseline, and during that phase, the solutions more often than not turn off all their alerting capability until the baseline has settled. And then that will go along for a while. And then as the question mentions, there'll be a policy change that alters the behavior. That often causes a lot of alerts to be generated, at which time the system is put back into a training mode where alerts are suppressed until the baseline restabilizes, and then is allowed to alert again. So that is a issue with a lot of the anomaly detection capabilities, is while they can adapt to the new changes in policy, every time it has to do that, you get a little bit of a blind spot while it retrains. And that can, depending on how much of a difference it is, take anywhere from a couple of days to a couple of weeks for those baselines to stabilize.
Next question. How do you protect from internally generated faults?
How do you protect from internally generated faults? So I'll admit I don't fully follow the question. I'll give you a bit of an interpretation of what I think the question's asking, and maybe that's around how do you deal if you're using the analyst feedback and they give you bad feedback? So they say something's a false positive, it really was malicious. So there, the question, there's a level of trust in your labeling that all classification algorithms will assume. But some algorithms are better at handling mislabeled data than others. There's even some evidence in the literature to suggest that for things like decision trees, that having a small percentage of mislabeled data, and usually you're talking like 0.1, 0.2% of the training set, will actually improve the overall algorithm performance because it prevents overfitting, which is basically a problem in model generation where it too tightly fits the training set and then doesn't do that well against the test set. So when we're building these models, we always reserve a portion of the corpus of samples that are labeled for testing and then train on the rest, but always express the quality of the model in terms of how well it performed on that test data set. So again, a good data science approach would detect that behavior. You know, if the stamp of the training set was somehow poisoned, it should be able to detect that. If it's small enough, now if it's a very gross behavior, then you know, it will cause the model to drift to meet those new labels. So it's something that the data science team has to watch out for. And otherwise also the selection of the algorithm itself can help make the solutions more robust to that.
Okay, now here's a lengthy question. Just want to make sure I get it completely clear. As far as my knowledge of machine learning and cybersecurity is concerned, I think machine learning algorithms are computationally complex and involve huge latency. So for real-time cyber warfare, machine learning-based intrusion detection systems, IDS, are unable to detect a threat, preemptively. I'm not sure if that's a question for you, Scott, but if you would like to elaborate or provide more detail.
I would definitely like to take it. Yeah, sure. So again, it depends heavily on the approach taken and exactly what the machine learning algorithm is doing. So the machine learning complexity is mostly in the building of the model. Once a model exists, particularly on the classification side, which is what you would normally see at the NIDS level, there are a couple of gateway solutions doing anomaly detection for outbound traffic, but most of the ones out there doing machine learning are really focusing on content analysis and deciding whether it's good or bad. And then for those, you know, the complexity is really based on that feature selection. So if the group building the model did a good job in the feature selection phase and the feature engineering phase, and they selected features which were easy to obtain, then those can be operated at incredible speeds, easily hundreds of samples per second, much faster than even large. And just from our experience, you know, we have systems operating on multiple 10 gigabit per second networks, seeing tens of files per second, and have absolutely no problem keeping up with scanning each and every file through the machine learning based models. So it absolutely can operate at even really high line rates. Now, on the other hand, you can build models that can do nowhere near that. So it really has everything to do with the way the solution was built rather than the technology itself.
Okay, perfect. So next question is, what is the best between supervised and unsupervised for cybersecurity?
So a good question. I actually get that one quite a bit. And I always like to answer it. It's almost the same question you get, what's the best between gateway security and endpoint security? And the answer is you need both. And they both play a role in a good layered defense and an overall defense in-depth strategy. The supervised learning is very good and well suited for early phase attacks, that pre-breach attack analysis of things entering into a network that might be malicious, doing content analysis. And anomaly detection is good for, again, that post-breach phase. where perhaps you're looking for deviations from baselines, unusual user behaviors for like insider threat detection. So they both have their role. And I think when they're used in the role that they're good at, they're highly complementary. And you should really look at what problem are you trying to solve, and really use the right solution to solve that problem. It's not really whether one is good or better than the other.
Okay. Next question is, similar to stock crashes, because of algorithmic investing, will increased reliance on ML lead to large-scale exposure to vulnerabilities? Excuse me.
So could you repeat the first part of the question?
Sure. Similar to stock crashes because of algorithmic investing, will increased reliance on ML lead to large-scale exposure to vulnerabilities?
Yeah, so that's an interesting analogy. The stock market is a highly coupled system, whereas if you look in cybersecurity, there's actually a lot of effort made to introduce silos of behavior, particularly within the defenses. So one of the biggest challenges in cybersecurity is even just sharing data. So to get something that would be so systematic as like you would see in the stock market of one system driving another system's behavior, I think just the decoupling we see in cybersecurity across enterprises would prevent something like that from happening. But it does come back to that whole moving defense concept, and that if different folks have different algorithms, different models, that would also give some protection, because you'll get a variety of solutions. And the majority of them should be getting it right, but the ones that are getting it wrong, not everybody will get it wrong. So there would be a voice in any sort of shared defense that would counteract the wrong. Whereas if everybody's getting the same model, you get this like positive feedback loop that could definitely potentially drive to blocking important behaviors or important content in the global system. So I do think just because of the nature of the cybersecurity business being quite siloed and decoupled, we wouldn't see the same things we do in the stock market, and then also around this idea of everybody being different, and most of the time only a small percentage of people or of algorithms getting something wrong, where the majority will get it right.
All right, Scott, how do you handle encrypted traffic coming out of the firewall?
So encryption is a whole other ball game, and certainly depending on where you're deploying machine learning-based solutions, you may or may not encounter it. If you're at a network gateway solution, obviously it's a bigger concern. If you're at an endpoint, and there's plenty of machine learning solutions that operate on endpoints, they sort of see the content or even the log data prior to any encryption being applied. So that's certainly one answer. And even at the gateway, there are technical solutions both at the tapping layer, so how you're extracting the packets from the network. If you're using a packet broker, often those have the ability to do SSL or TLS intercept. Basically, they man in the middle of the encrypted session and then allow for security inspection. The challenge there with encryption is, the same whether you're applying machine learning-based approaches as you are signature-based approaches or heuristical-based approaches or rules-based dynamic analysis. It's about getting visibility into the traffic more than it is about the detection technology. And it just has to be solved if you want to leverage detection on those flows. And like there are plenty of vendors out there that have those solutions.
Okay, next question, Scott. What's a new area of research on unsupervised or supervised machine learning algorithm on security?
So there's been a bit of success in the deep learning space. So deep learning, sort of the goal of it is to sort of alleviate the burden on the data scientist to figure out a really good feature space. What we'd like to be able to do is push that part into the learning algorithm itself and be able to give a very basic representation of the sample to the learning algorithm and it figure out the feature space and then learn. That's sort of the goal of deep learning. It leverages artificial neural networks, usually multi-layer neural networks, and it's seen really good success in areas like image recognition. And so I think one of the hotter areas is trying to figure out, hey, can you apply that technique and get similar type of results in cybersecurity? And I think it's an ongoing area of research. There are some groups that have had some promising results. But I would say today it's still not the most effective technique, but definitely an interesting one. And another area is around hardware accelerated machine learning. The two are not unrelated. Most of the hardware acceleration around sort of continuous learning problems maybe allow you to keep up more with the learning samples, use more samples, train faster, reduce baselining times, and then leverage things like GPUs on the hardware side to do that. Particularly the backpropagation algorithms used for training artificial neural nets are well suited for highly parallel computation.
Okay. Next question we have here is, have you seen examples of ML-based security solutions having their own or having their training being deliberately poisoned to weaken their effectiveness?
So have I personally seen it? No, and I know people have talked about it. I've read papers where they've experimented with it. And some of the outcomes of those papers I actually mentioned that certain algorithms are more or less robust to that sort of data set poisoning. Depending on the technique, supervised versus unsupervised, the supervised ones, because most of the training data is still controlled by a third party, the vendor, typically data science team, it's really, really difficult to poison that. The unsupervised one is a little bit easier in that if the adversary is in the network and they're aware of the fact that the network is being monitored by an anomaly detection system, they can begin to try to drift the baseline. Again, it can be pretty difficult to do, and I've not really seen operational stories around anyone having successfully done that, but certainly it's been written about and theorized that it's possible.
Okay, well, unfortunately, we have run out of time. I'd like to thank Dr. Miserandino for his information and for the presentation as a whole. I'd also like to thank BluVector, IEEE Computer Society, and a special thank you to the audience. Thank you guys for participating and attending. Have a great day.